Good morning. My name is Greg Thane, and today I'd like to talk to you about the HTCondor philosophy. But not really the HTCondor or the Condor software suite philosophy alone, really the philosophy of high throughput computing in general. So imagine a world, to start with, that doesn't have HTCondor in it. Horrible, I know. In such a world, are high throughput ideas still valid? That's sort of the thesis of this talk. Now, when we start thinking about high throughput computing, we start with people. We don't start with computers or networks or megabytes or jobs or processes. We start with people because people have problems, and that's what we're here to solve. We're here to solve the problems that people have. And it's not necessarily a technical problem that we start with, but maybe more a social problem. For example, here's a person with a problem. This is one of our chemistry researchers on campus, and she's got more work than can be done on one computer. So how do we solve this? Well, before we do, we first have some high throughput lemmas that we need to start with. We assume that there is a large amount of work, but this work can be broken up into smaller, mostly independent jobs. And our goal is not to optimize the runtime of any one of these jobs, but rather to optimize the time to finish. That is, really cared about the time it takes to get to the last instruction of the last job in this set of work. And these jobs, they may communicate via files, but that's it. They're not tightly coupled, they're loosely coupled. The output of one job may be the input file of another, but that's the primary way in which they communicate with each other. And those are kind of the basics of how we think about computing. So this focus on job leads to what I call the job nature. That is to say, there's certain aspects of jobs, and here are some of the key ones. That jobs have an identity. In our case, it's a number by which we can refer to them. We can submit a job, we can refer to it by its number, we can remove it, we can ask questions about its resource usage by its number, but a job has an identity. And jobs descriptions are completely specified in a file or maybe a little bit of Python somewhere. Some people like to call this reifying or making a real, from the Latin word re. And jobs, this description is also extensible. So while there are many built-in attributes of this description that come with the system, maybe the name of a job or its executable or its input files, there are extensible things that only the researcher knows. There are aspects about that job that we want to carry along with the job that aren't standard in the system. And fundamentally, jobs have a life cycle. And that life cycle is there's an input sandbox, which gets transferred to the job, an execution, which reads from that input sandbox and creates some scratch directories and maybe some output. And output is returned back to the submitter. And this is the job lifecycle. This is very important in the notion of job. So after we have jobs, the existence of jobs leads to, naturally, the existence of an access point, what we call an access point, which is merely a place for your jobs. And the access point keeps track of all the jobs that you care about. It keeps track of work that has yet to be done, work that has already been done, and maybe an order in which to do the work. But the access point really is the holder for all of your jobs, all of your work. And this access point isn't some skeuomorphic interface like Microsoft Bob here, not at all. An access point is just a computer. Or, it's not quite a spreadsheet, but if you think about an access point as a spreadsheet that holds data about all your jobs in a secure way, you won't be far off here. And here's an example of maybe some of the attributes that your job might have. We have the job number, which is part of the identity we talked about. Status command and arguments are attributes that perhaps come with the system. And maybe our chemist here has a beaker number that isn't standard part of a job management system, but is part of this extensible schema that she wants to add to keep track of for all of these jobs. It's important for each of these jobs, and this extensible nature is an important part of the job nature. So principles about the access point then is, first of all, it must be robust. And by that we mean we can't guarantee that it won't crash, but when it crashes or when it loses power or when it gets rebooted, it won't lose your jobs. Once your jobs are submitted to it, it is responsible for it and it owns it. The access point is yours so that a person controls the access point and has full authority over the policy there. And that may be different policy in other places in the system, but an access point is a place for a user's policy. We would like the access point to be scalable, to hold lots of these jobs, because these jobs are independent. We want to be able to hold tens of thousands of these. So it's important that we're scalable. We can hold a lot of jobs in a single access point. To the degree that it's not scalable, there's obviously always a limit to scalability. It's also can support an access point can support more than one schedd, or more than one access point can be federated together. So you can have more than one in a Condor system. And it owns a job policy, so it makes the decisions about jobs. So let's escape our world that didn't have Condor in it and return to a world with Condor. And an access point in Condor terms really means a Condor schedd process. So on Linux, it's a Unix process, or on Windows, it's a Windows process called condor schedd, which is a service that runs. And because we want the service to be robust, and because we believe in the Unix philosophy, we try and keep one Unix process per service. And this gives us good failure semantics. So when it crashes, if it crashes, it takes out the memory, and the kernel will clean up after it, and we can restart it in a nice, clean way. And each of these Unix processes has a very distinct responsibility, which we'll get to in the rest of the talk. And we may have many of these processes per machine, and we're okay with that because each of these processes gives us a nice failure domain. So on the access point, we start with a schedd, and when the schedd is actually running a job, it runs a different process, one per job, called a shadow. And this shadow is responsible for running the job itself. We have one running process, one running shadow process per running job, and it is responsible for acting on the wants and the needs of that job, perhaps remotely as the job is running somewhere else. This is a little expensive, but gosh, it is so worth it to have this failure semantic and this one place, this running process, the shadow, that is a representation of the job's wants and needs. And should we run out of resources on the access point, we can scale by adding multiple access points. And this allows us to submit locally and run globally. So in a high throughput system that has lots of users who are maybe spread about campus, we can put an access point near to each of these users and give them control over their own policy there. So this allows the submit to be near the user, which is very, very powerful and a very good way for us to scale. Now, because we want to be robust, this also requires a parent process. And the way we do this in Condor is we have a small Condor master process that runs on every Condor machine. Every Condor machine, no matter what its role, has a Condor master in it. And it is much like init or systemd in that it starts and restarts processes. If a child process, if it exits or crashes, the master will restart it. And it accepts commands, authenticated commands over TCP. So the master can be controlled remotely to tell the daemons under it to go on or off. And it runs the Linux kernel tuning script also. So it also adapts the machine to set various Linux kernel methods that have set. And all these things together mean that the master manages processes. And management is a term that we use a lot in HTCondor. And it means a lot of things to us. It doesn't just mean to be able to create processes, but more importantly, it means to be able to clean up after ourselves. And this is often more difficult, cleaning up after yourselves, being able to remove a process that you've created, or better yet, to remove not just a process you've created, but all the processes that it's created recursively, is a very important part of management, and something we work hard to take care of. Not just the removing and the cleaning up, but also even measuring what you create is a very important part of management. We try and manage everything, and we try and keep track and measure all these things that we create, be they jobs, be they access points, or other points which we'll get to later. And in some cases, we want to be able to limit what we can create. So every machine obviously has a finite amount of resources that it can use, and we want to be able to put limits and circuit breakers in, so either jobs or the Condor services themselves can't overwhelm a machine, that we would rather have a machine be limited before it gets to the point where it exhausts resources and crashes. And this reliability is really one of our primary goals in Condor. So we can often make Condor fast enough without polishing screws or sacrificing any reliability. And in a lot of places where we have a choice, we often err on the side of reliability instead of performance. And we find by getting the architecture right, we can scale in ways, for example, as we said before, by adding access points where we don't need to polish all the screws and optimize within an inch of parts. So given that we have an access point, can we run jobs there? Can we do work there? Well, yes, we can, but they're a finite resource and they may not have enough power. And the access point may be shared, so it's really important that we be a good citizen. So this implies the existence of what we call execution points, or the primary place where the work actually happens. Um, and these things, these execution points, because they may be heterogeneous, they may be different, and the job may be a guest there, it needs to clean up. We need to be able to attach these to the access point and maybe later detach these. So given that we have an access point that has all of our jobs, we want to be able to attach one or more execution points and tell this access point, oh, here are places where maybe you can run your jobs on for now, and then maybe later detach them and say, not so much anymore. And in general, we want to be able to run on all possible nodes that we have access to, and that fits. And this, because we have a very large number of these worker nodes, these execution points, this implies that they're heterogeneous, and they could be pools from a foreign place. They could be heterogeneous because they have a different configuration. Maybe some machines are have a configuration that prioritizes them for one group or another. Or they could have different physical configurations. Maybe some have more memory or GPUs that others don't, or large file systems or shared file systems. So in general, these execution points can be very different from each other, and we do not assume that they're the same in any one of a number of dimensions. So just like there's a schedd that runs on the access point, the condor start D is the main daemon that runs on execution points. And it represents the policy of the machine, or maybe the machine's owner. And it creates the abstraction of slots, which are really places for jobs to run. And because the start D has policy, maybe a start D's policy is I only want to run jobs from the physics department. And because the execution point has policy, which may be a little bit different than the start D's policy, they could conflict. And sort of a question you might ask is, well, in the case of a conflict, whose wins? And the condor philosophy states very clearly that it's always the machine's policy that wins in the case of a conflict. And this is fundamentally because the job is a guest on the machine, and the machine can come and go, but the value of the job's policy always wins when there's a conflict over the execution point. And the start D's mission statement is really quite simple. You may think of it as kind of nearsighted. It only has three inputs. It looks at itself, the machine it's running on, the machine that it is. It looks at any jobs that are currently running on that machine, if there are any, and perhaps one candidate running job. It doesn't know anything else about the rest of the system. It doesn't know about any other jobs that may be on an access point. It knows nothing about any other start Ds or any other execution point. When it makes a decision, these are the only three inputs that. And given this, there's just a few things a start D can do. It can decide to only run some kind of jobs. It can say, well, I will only run jobs from the chemistry departments, or that are marked from beaker 3 in the case of the extensible jobs. It can preempt a currently running job for another job. You can tell it to only run one or some limited job of some type. You can say, well, this start D, it for whatever reason can only run 3 jobs of this type, and you can put a limit on that. And it can expose and match custom resources. So just like our jobs have an extensible syntax where you can add that beaker number, so too can the start Ds. For example, maybe a start D has a room number that it's in, or a rack number, or I don't know, the date it was purchased. All these are examples of extensible attributes that you could add to the start D that could be used in policy. But the start D itself doesn't run the job directly. It creates and manages, in all the ways that we talked about earlier about management, a child process called the starter. And the starter itself is what manages the job. So just to be clear, because our terminology is a little funny here, the start D manages the machine, but the starter manages the job. So when a job starts on an execution point, the start spawns a starter, and the starter actually runs the job itself. There's one starter per job, and that means there's always one starter per slot. So the responsibilities of the starter are to manage the running job in the machine. It creates the environment for the job, not just the environment variables, but a scratch directory, um, and command line arguments and all this stuff. It manages the job, it monitors, it reports job resource usage like memory usage and disk usage and CPU usage. And of course, it cleans up after the job. Remember, everything that we create, we also have to clean up after it. And if need be, it transfers the input sandbox to and from the job. Now we can get these sandboxes to the job via shared file system or explicitly via file transfer. And whenever there's an opportunity, we always prefer file transfer. File transfer in Condor is managed. And again, this is this managed word we talk about a lot, which means that we keep track of it, we measure how well we're doing, we potentially limit the amount of concurrent file transfers if it looks like we're going to overwhelm one machine or another. File transfer is explicit, it's declarable, and portable, which means that a job that explicitly declares its input files, as opposed to picking them off a shared file system, is much easier to pick up and send that job to a remote pool than perhaps one that relies on a shared file system. And this leads to sort of what I call the two-faced nature of Condor, and that is we have split execution. There's some responsibility that happens on the worker side, like this management directly at the job, the middle memory, and some responsibility that happens on the access point on the submit side. And we encourage to have different configuration on both sides and to encourage admins to always think about which side any given functionality really has responsibility for. There's a lot of places in Condor where any particular policy could be implemented on either one of these two sides. But given the responsibility for who wants to implement this policy, it really belongs on one side or another. Take, for example, the desire to limit memory. Maybe we want to have a memory limit for, say, of 1 gigabyte. We want to not let a job use more than 1 gigabyte. And we can implement that in Condor on the start side or on the submit side, but where to do it kind of depends on what actually is going on. If you want to limit memory to 1 gigabyte because you know that there's a bug in the job and sometimes it allocates too much memory, and you want to say, if I've gone beyond a gig, I know there's a bug in the job. Well, clearly that's an aspect of the job, and the submit machine is responsible for the job. So maybe that's policy that belongs on the submit machine as part of the job. If you want to limit to 1 gigabyte because you know that the machine only has 2 gigabytes, and if you allocate more than 1 gigabyte, then the machine's going to start swapping and get to a bad place. Clearly, that's the responsibility of the start D, and maybe that's an example of a policy that might go on the start D side. So putting it together, we've talked about 2 of the 3 sides of Condor. We talked about the access points on the left here. We talked about the execution points, which are attached to the access point. And there is one more side we haven't talked about, the central manager, or the middle point, if you will. And the central manager really is composed of 2 different parts. The first is the collector. This is a central in-memory lightweight database. Every daemon, every service in Condor reports itself as a class add to the collector. And this is what the Condor status command queries. The interesting thing about the collector is it's stateless, which means that when it crashes, it loses everything from memory. So the protocol is to always be updating it. When every daemon, say the start D or the schedd D, sends its status to the collector, it does it periodically every few minutes, so that if everything is lost in a collector crash, it will just get refreshed and repopulated. So it's not the central point of failure that you think it might be. And we have this nice lease protocol between the collector and its clients, so that on every update, the client sets the time at which it was updated, and the collector notices periodically when ads are getting stale, and if an ad hasn't been updated in a while, it gets removed from the collector. So this gives us this nice property that if a daemon crashes without the opportunity to tell the collector that it's fixing to crash, it's about to crash, eventually that ad will get removed from the collector without any manual intervention, which is kind of a nice property. The final piece I want to talk about on the central manager is the negotiator, and this is kind of the other half of scheduling. And it acts maybe not slowly, but deliberately, and its role is to balance the execution points by user so that it keeps a fair share of all the worker nodes by users or maybe groups. So in Condor, we have kind of this two-phase scheduling. The slower phase that the negotiator does where it rebalances and assigns resources to schedds, and then a faster pace, a different cadence that happens on the access points in the schedd. So the schedd can take a start that has been given to it by the negotiator and reuse that several times to run different jobs on it in sequence without needing to talk to the negotiator. And because this negotiator isn't really a single point of failure either, should the negotiator crash, the schedds, the one or more schedds in the pool, will keep running with the matches that they've been given by the negotiator. So that's kind of a high-level overview of high throughput computing, HTC. And with Condor, we can do not just HTC, but dHTC, or distributed high throughput computing. And that's, put simply, this idea that we take the idea of high throughput computing and just sort of extend it one more. So we have a pool like on the left and a pool like on the right. With dHTC, we can forward jobs from one pool to the other. So we don't just have these islands of high throughput computing, but we can link them all together to form a greater federation of computing, which is kind of a neat trick. And that target pool may not necessarily even be an HTCondor pool. With dHTC, we have mechanisms to send jobs to other batch systems, even if they're not HTCondor. So in summary, people have problems. We hope that maybe HTC is one small way that people can actually solve problems. So thank you. That's my talk for today, and let's continue discussion. Thank you very much.